are going to discuss about logic gates. First, what are logic gates? Logic gates are the basic building blocks of digital circuits. Logic gates are the electronic circuits that take binary inputs, either 1 or 0, and produce a binary output. Basically, logic gates are of two types. We have basic logic gates and universal logic gates. First, let's discuss about basic logic gates. In basic logic gates, we have three, which are AND, OR, and NOT. First, here we have AND gate. What is an AND gate? Here we have the representation of the AND gate. AND gate simply represents multiplication function. All the gates here are designed using the transistors. We have a truth table here. As I told before, AND represents multiplication. If you take the input as 0 and 0, 0 into 0, you're going to get the output as 0. If the input is 0 and 1, the output is going to be 0. When the input is 1 and 0, the output is again 0. When the input is 1 and the output is 1. So indirectly, you can say that if at least one input is 0, then the output is going to be 0. Here, this is the truth table, which represents the inputs and outputs of AND gate. Next, we have OR gate. This is the representation of the OR gate. An OR gate simply does the function of addition operation. If the input, let's take the input A and B, and let X be the output. If you take the input as 0 and 0, you're going to get the output as 0. When the input is 0 and 1, the output is going to be 1. When the input is 1 and 0, the output is 1. And the input is 1 and 1, the output is again 1. You can simply say that if at least one of the input is 1, then the output is going to be 1. Here in the example, you have input as 10110. Here you have 1, so at least you need to have single 1 as an input. So here we have 3 ones, so the output is going to be 1. Next, we are going to discuss about NOT gate. NOT gate generally works as a complement. Here is a block diagram or representation of NOT gate. It is represented by a triangle with a small circle at its end. If you give the input as A, you're going to get the output as A complement. Simply, if the input is 0, the output is going to be 1. If the input is 1, the output is going to be 0. These are the basic logic gates. Now let's go into universal logic gates. Before we go into universal logic gates, there is a gate called as buffer gate. Buffer gate simply stores the data and transfers the same data. For example, if you give input as 0, and it's going to store the same thing 0. If the input is 1, it's going to store the same thing as 1. Here we have X, which represents the buffer data, and this is the truth table for the buffer gate. Next, we have XOR gate. XOR gate is a special kind of gate. In this, if all the inputs are same, the output is going to be 0. In all other cases, the output is going to be 1. Here is the diagrammatical representation of XOR gate. Simply, the equation of XOR gate is A dash B plus AB dash. Here you can look at the truth table where you have input as 0 and 0, which gives you the output 0. As you have all the inputs same, you'll get the output as 0. And for 1 and 1, the output is 0. And in remaining cases, the output is 1. This is about XOR gate. Next, we have XNOR gate. XNOR gate is complement of XOR gate. If XOR gate is 0, it is going to give its complement in XNOR gate. Here you can see the representation of this gate. And here is the derivation of the equation for XNOR gate. X is equal to A plus B whole complement. If you're going to expand this, you get A dash B plus AB dash whole complement. On deriving it, you will get AB plus A dash B dash, which is nothing but XNOR gate. This XNOR gate is represented by this symbol given here. Next, look at the truth table. Generally, in XOR gate, if two inputs are same, we are going to get the output as 0. Here, it's reverse. When two inputs are same, you're going to get the output as 1. If you look in the truth table, when the input is 0 and 0, the output is going to be 1. When the input is 1 and 1, the output is 1. And in other cases, the output is 0. It's exactly opposite to XOR gate. Next, let's discuss about universal logic gates. There are two universal logic gates which are NAND and NOR. These are called as universal logic gates because they involve all the basic gates, which is AND, OR, and NOT. Let's discuss about NAND gate. NAND gate is complement of AND gate. NAND gate is going to perform the same multiplication operation, but it's going to consider the complement of the result. This is how you represent NAND gate. It's simply using a D shape along with a circle at the end. When you take the input as 0 and 0, generally an AND gate is going to give 0. But here it's an AND gate, so you get the complement of that. So when you get in AND gate as 0, but in NAND you're going to get it as 1. If you look at the truth table, when the inputs are 0 and 0, the output is 1. When the input is 1 and 0, you get output as 1. When the input is 0 and 1, the output is 1. When the input is 1 and 1, you get the output as 0. So simply speaking, when at least one input is 0, the output is going to be 1. In other cases, it's going to be 0. Next, we're going to discuss about NOR gate. NOR gate is complement of OR gate. OR gate is going to perform the operation of addition, and NOR gate is going to do the complement of it. This is how you represent NOR gate. It's just adding a circle at the end of OR gate. If you look at the truth table, when the inputs are 0 and 0, you get the output as 1. When the input is 0 and 1, you get the output as 0. When the input is 1 and 0, the output is going to be 0. When the input is 1 and 1, the output is going to be 0. So you can say that when at least one input is 1, you're going to get the output as 0, and in other cases, the output is going to be 1. So this is about logic gates.